My name is Rigel. I am a senior machine learning engineer at Clarifai, and today I'm going to be talking about something that is near and dear to my heart, and I think it's near and dear to a lot of our hearts, which is data. And it's specifically when data can go wrong and how it can affect your life. So, as the title of my talk, The Unreasonable Deceptiveness of Bad Data. Cool. So, just a little bit of background to hopefully motivate this talk a little bit. I work at Clarifai. We are an AI platform for computer vision. We got started when our founder, Matt Zeeler, won ImageNet back in 2013. He was using, one of the sort of early people in the kind of modern era to use deep learning for computer vision, and he, won like the first 5 places in ImageNet and used that technology to found the company. And I think he gave a very popular talk at this conference a couple years ago. And since then, things have been going well. We're over 100 employees now. And so our products, just to, some people aren't super clear on this, our products basically break down into 3 major categories. The first is predict. And this is sort of what it sounds like. We have a suite of models that are, image classifier models, image detector models that you can call our API with. You can send your images to us and we'll send you back predictions. And you can kind of see that on the right here. This is literally just a screen grab from the demo on our website. So you can go and try all our models in real time. We have another product called Create, which is sort of interesting. This is our product that allows you to create your own image classifiers, just in case none of our models fit exactly your use case. You can upload your own data with your own tags and train your own stuff, and we'll sort of see a little bit more about that later. And we also have Search, which means that we allow you to upload your database of images to our platform and do visual searches over them to find things that are sort of visually and semantically similar. So that's cool. So at Clarifai, I'm part of the applied machine learning team. And I find that when I tell people this, the impression that they get is that, like, this is kind of what I do, right? Some kind of like Inception, deep ResNet 1000 LSTM kind of situation, right? Models to learn models, and like I'm BFFs with Jan LeCun, right? So that's cool. This stuff is really important, obviously, and it was sort of the inception of our company, and it is really interesting. But like the truth is, for me, and I think for a lot of people that work in this space, that's not really the important part of my day-to-day. My day-to-day looks a lot more like this, right? I'm basically looking at data. Data used to train models, data used to evaluate models, data used to tune models, and just sort of getting an understanding of lots of data sets and the way that they affect our production systems. So hopefully that gives a little bit of background about why I want to talk about bad data today, because really this is the thing that gets in my way, I'd say, the most out of basically any challenge in our technical space. So just to be a little bit more concrete, the applied machine learning team, what we're really responsible for is machine learning in production. If there's a product that uses machine learning, which is a pretty common situation to Clarifai, the AML team is on top of it. We're responsible for making sure that the models are up to snuff, making sure that they're evaluated well and that they're cutting edge, state of the art, and efficient and scalable and all these things. So I like to describe us as sort of the link between research and product. Sort of unfair because we also work really, really closely with back end and front end and basically everybody else. But it sort of involves taking the things that we're researching and the things that are in academia and making sure that we can put them into products. And that involves things like training and evaluating and deploying models, tuning algorithms that maybe are unsupervised, things like visual search. It can even involve actually getting data labeled and making sure that the efficiency with which we're labeling that data is very high, and the cost is low. And so within this is sort of where I sit, training, evaluating, and deploying models, and this includes also working on our custom training platform, which, like I said earlier, is where you can actually train your own classifiers to fit exactly your taxonomy and your domain. So cool. So this is what I want to talk about today. These are the questions that I'm trying to answer. And these are also questions that I found myself trying to answer, in my time, both at Clarifai and sort of in general, working with data. So the questions are, what is bad data? How do we actually define it? What's so bad about it? Kind of why should I care if my data is bad or not? How do I expose bad data? And then hopefully the silver lining, which will be how do you make good data, bad data into good data? or is all hope lost? Cool. So what is bad data? First of all, it's important to motivate why we actually need to talk about this. The answer is because we need data, and I think all of us as data scientists here know that. But I really like this chart to motivate exactly how important it is. This is taken from a paper that came out of CMU and Google called "Revisiting the Unreasonable Effectiveness of Data in the Deep Learning Era." And essentially, the question, as I understood it, that they were trying to answer was, how much data is enough data? Like, if we collect enormous amounts of data to feed these very data-hungry machine learning algorithms we're working with now, at what point can we stop? At what point does the model stop getting better? And then they have this chart, which shows that they collected this data set with 300 million examples in it, which is pretty large for a data set. And they don't really find the point. It just kind of keeps going up. I mean, it's going up logarithmically. You can see it's like an exponential scale at the bottom, but it doesn't really show signs of stopping. So it really matters that we have data. But what do we do with that data? So the way I hear a lot of people talking to me about this, especially when they're, maybe they're not super familiar with the field, or maybe they're not super in depth with it. But even when they are, they talk about it like they understand it like a blender, right? You have like some data blender, and you put your data in the data blender, right? And if all goes well, you come out with some kind of a delicious data smoothie, right? Everything's going fantastically. So that's actually great. So that works a lot of the time. This analogy is pretty much right. Like, a lot of the time, you can really just throw it at your algorithm and get something that you want. But it kind of depends on like your data looking like this, right? You have to make some assumption that when you open your data pantry, you're going to get a lot of fruits and vegetables and things that are going to go great in a data smoothie. But what if something like this is in your pantry, right? And maybe it's not obvious, it's not to say that this is a bad thing, but you probably don't want to put this in a blender and get a smoothie, right? So that's sort of the point here, is you have to know what exactly you're putting in your algorithms. So the way I like to break it down is basically with two definitions. So the first way I think about bad data is there's one kind of bad data that I call honest bad data. And this is the data that we all are very familiar with. This is data that's bad, and it's bad, right? The models are bad, or the labels are bad, they're noisy, something is wrong with the images, right? Something is terribly wrong with this data, and it's super obvious right off the bat. On the other hand, though, there's something quite a bit more sinister that I call deceptive bad data. And this is the data that's so bad that you think it's good. And so what does this mean? So I'll have a couple of examples here to hopefully sort of illuminate that. So what's so bad about this? Well, why don't you want yourselves in these situations? Well, the first obvious answer is, if you have bad data, you can have bad models, right? You can have a situation like this for the uninitiated, right? This is the worst you can do on both of these performance curves, right? You have a precision recall with an the elbow at the very bottom, and basically a perfectly random classifier. This is not what you want. But at least if you have something like honest bad data, where the data labels are noisy, you will get a situation like this, and you will know that your data is bad, and that your model is bad coming out of it. But what if that's not necessarily the case? What if instead of knowing that your data is bad and the model you're training is bad, you instead have some kind of a false confidence about your model? And this can happen more with the deceptive bad data case, in my experience. And often it happens when your test set is not exactly the right thing to actually evaluate your model on. It doesn't actually reflect the real world. So just to give like an example of this, just a little story about something that happened to Clarifai. We were working on a classifier for a moderation use case. It was an e-commerce company that we were working with, and they wanted to make sure that certain things weren't being sold on their website. Makes a lot of sense. This kind of thing happens all the time. People try to sell stuff that you really shouldn't sell. And so one of those things that they wanted to find was license plates. So we thought, okay, that's great. So we collected a bunch of license plate data. This is pretty straightforward, right? If you've trained image classifiers, you can tell license plates are pretty visually distinct. You know, it seems pretty straightforward to train a model to recognize license plates. So we did that, and we had really great performance numbers. And you know, this was one out of many concepts that we were shipping to them. So we thought, okay, great, we'll send this off, and hopefully everything goes well. And then we heard back from the customer, and they said, hey, something is terribly wrong. Your license plate category is firing way too much. Like, we know there are license plates in this data, but like it's firing on like 10% of our total stream or something like that. Like, there are definitely not this many license plates in our data. So okay, fine. We looked into it, and what we saw was that, of course, when we started looking at what this model is actually predicting license plates on from their data set, of course, it didn't look like this, right? It looked a lot more like this. Obviously, cars have license plates on them. This e-commerce marketplace happens to sell cars. And that's just something that we didn't take into account when we were initially evaluating our model. We were trying to evaluate, you know, can we find license plates? And the answer is yes, but in all the wrong scenarios. So this was a big learning point for me. So another way that bad data can affect you in sort of deceptive ways is through machine bias. And this has sort of been in the news lately. This is a topic that's really starting to pick up steam. And this can be essentially when, you know, a model that's trained can have unintended consequences and affect, you know, often sensitive sort of demographic variables in the real world in ways that you really didn't want it to and really didn't expect it to. So one great paper that I like to talk about is this paper that came out a few years ago. It's called Man is to Computer Programmer as Woman is to Homemaker, Debiasing Word Embeddings. And so if you're not familiar with word embeddings, essentially the idea is, of course, you have a vector that represents every word, and you try to use these vectors to create your classifiers and encode your text with. So that's great. And there's this really great party trick you can do with them where you can do all these great analogies. So you can subtract vectors and sort of get these really semantically meaningful things. Like, they find that if you subtract the vector for man and woman, you get a vector that's very, very close to the vector that you get when you subtract king and queen. So this is cool because it sort of indicates that, you know, the model is encoding something about the difference between man and woman. Awesome. But that can go awry. And what they found is it's not usually as innocent as this. They found also examples like this, where the difference between man and woman was also approximately the difference between computer programmer and homemaker. And obviously, this is not something we want, right? And this isn't just a one-off case. They managed to find tons and tons of these analogies in sort of the public Word2Vec model that, of course, many NLP systems and productions are reliant on. So if this exists in the underlying algorithm, then likely this exists in the algorithms that this was used to make. So this is the kind of thing that's just sort of lurking just below the surface. And of course, nobody, when they were training Word2Vec, you know, was specifically trying to encode these analogies, but this was sort of latent in the data, and training a model to create these analogical structures actually managed to expose it. Another example of this is something that was in the New York Times recently. The title is "Facial Recognition is Accurate If You're a White Guy." And what they essentially found was that for a lot of public facial recognition APIs, they are much better as the further you get along the scale of skin tone that they defined towards the lighter spectrum. So this is obviously a terrible thing. This is something that I would hope that, and I would assume that nobody intended for their classifiers to do, but because maybe of some latent bias in the data that they train the classifier on, this is exactly the kind of thing that can happen. It can be really difficult to expose. Cool. So far, right? What have we talked about? When you have honest bad data, you can get these bad models, and you know, this is sort of the classic case of when you know that your data is bad. But in the more sinister case, you can have false confidence in your model's performance because you're not evaluating it in the right way, or even you can have these horrible bias problems in your models that are really hard to expose but affect lots and lots of downstream technologies. Cool. So next up is this question of how do you actually expose your bad data? So now you're worried about bad data, and you have a data set, but what do you do if you want to find it? right? So my answer is essentially use tools. There are lots of really, really great tools out there for evaluating your data set, for looking through your data set, for searching over your data set. If you're wondering where the plug is coming, this is it. We have this tool at Clarifai called Clarifai Explorer, and this is what I use all the time to be evaluating models and evaluating data sets and sort of looking through things. So what are some of the things you can do with this tool? And of course, this is not the only tool. This is just what I am familiar with, so this is what I can talk about. You can do visual searches over your data set. You can display labels that have been assigned to your images as you uploaded them. You can train models in this platform, and you can search with those model predictions on that data set. So this is really great if you want to do a sort of really quick, continuous feedback loop for development of machine learning. And so I have this link here that we will try to click. Can we see? All right, great. So I'm going to attempt a live demo here. I also have a backup video in case I chicken out, but I'm feeling lucky, so here we go. So far, so good. Do not save, no. Awesome. So this is essentially it. This is the tool. And what you can see here is we have what I call an application, or what is called an application, and it basically sort of represents a data set that you've uploaded to our platform. And this is just like a toy example. This is open images. I think it's like I just uploaded like 20,000 images from the data set just to sort of like, let us see on a high level what's going on here. So this is, some preview of some of the data. Like I said, you can do visual searches. So if I say wanted to find other examples of images that look like that car, I can just hit this guy, and it'll show me things that are visually similar. And again, this is within the 20,000 images that I uploaded to this car. So that's really awesome, right? That seems really useful. So what can we do here? Well, say that, for example, we want to make a model, a new classifier based on this data that differentiates between fruits and vegetables. Pretty straightforward. So let's give it a name, right? I know because I've done this already that Open Images has a concept for fruit in it, and it is here, and also one for vegetable. If I could only scroll, that would be great. Oh no. Okay. Great. All right. Awesome. There's a lot of concepts in Open Images. So cool. So we've got this new model. Two concepts, fruit and vegetable. This is just things that were pulled in from the data set. And so this is just all the data. You can see there's about 400 or so examples from each. How is this rendering? Oh, it's doing pretty well. OK. So we can train the model. This doesn't take very long. Great. So model's trained. That's awesome. So let's see how we did. We can hit this, and what this will essentially do is it'll take the data that I used to train the model, it'll split it up 5 ways, and it'll do 5-fold cross-validation. So this takes a little bit longer than training, but not that long. So awesome. So this is the performance of the model. Got a little confusion matrix here. You can see we have like 70 recall total and like almost 90 precision. Not bad for 45 seconds of work. But if I actually cared about this model, I might want to look into exactly what's going on here. So cool. So we can go back to the data set. And what we can do now is we can use this model that we just trained to search over the data. So what I'm doing here is I'm basically saying, OK, take this model, this concept that we've trained with this new classifier, take the fruit concept, and see like what is predicting highly on fruit. So this seems kind of reasonable, right? We have fruits, lots and lots of fruits, mostly on plants. We also sort of have a lot of these like flowers, right? Like here, we have a flower. We can actually get predictions from our general model here. We have some flowers and things like that. And these are being predicted pretty highly as fruit. So that's not great. So what can we do? Well, one thing we can do is we can try to isolate those examples. So we can also, in addition to searching with concepts that we've trained on, we can also use concepts from the general model, and we can combine these queries sort of like this. So if I want to search for flower, now these are things that are labeled as fruit and they're labeled as flower. So these are the things that are basically confusing our model. So that's awesome. So these are pretty much all flowers. But if you look at individual examples, there's super high probability fruit. So we can just take a bunch of these. Oops. Okay. And we can label them with a new label. Something like fruit negs, right? Like fruit negatives. Cool. So now we go back to our model. And we have this new concept, fruit negatives. So we kind of want to train these against each other so we can flip the switch to make it use a softmax in the final layer instead of just sigmoid on every single concept. We can retrain. Model is training. Model is trained. And so what happens is now when we search for fruit, hopefully this looks better. Pretty embarrassing if it didn't. Cool. So something apparently went wrong when I did that, right? This is exactly the kind of thing that can happen, right? But now I can go back and sort of maybe remove those negatives and like see exactly what needs to be teased apart between the fruits and like sort of flora in general. Okay, so great. So that's the end of fruits. I don't want to see that again. So what about vegetable though? What's going on here? So that looks different. Right? This is food. This is not really what we saw with fruit. So what does that mean? Like, these are vegetables, right? That's kind of good to know that exactly this is what was in my data was sort of vegetables on a plate. But does that mean that I want the fruit to also be on a plate? Do I want a food classifier, or am I trying to classify things in a market? You know? And so, like, you know, to me, when I'm doing this is of course just a toy example, but when I'm doing this in general, this is exactly the kind of question I end up answering because I am able to expose the nature of the data by quickly training and using these models and sort of just seeing exactly what they do. So cool, that is the demo. We'll be back. If I just do that. Okay, cool. So what did we just see? I was able to use this tool for understanding the training data, right, to a pretty effective degree. I was able to identify failure cases pretty fast. I was able to add a new concept with new data and retrain. And you know, the idea is rinse and repeat. You can keep doing this for you know, sort of until you have a model that you want, and that was, you know, in just a few minutes, right? So it's really important. And I'm not saying this is the only tool out there. This is just again, this is the one that I use. So it's really important to be able to use these tools and leverage these things in order to have a really, really good iteration process and expose hidden things in your data that you didn't know about. Awesome. So, okay, the silver lining. How do you make bad data into good data, or is all hope lost? So there's a few ideas. You know, I think everybody in this field is sort of working on this. Like, nobody has a perfect data situation. So there's a few ideas for how you can do this. First one is just use it. Like, don't worry about it so much. There's this very unfortunately titled paper, given the title of my talk, that's called The Unreasonable Effectiveness of Noisy Data in Fine-Grained Recognition. And this is from 2016. And essentially what they found was for a lot of these tasks where they have to do really fine-grained classification, they just do a big web scrape. And they have all this noisy data, and they use it in kind of clever ways. Oops. And what they find is they are able to blow the competition out of the water. So there is something to be said about not worrying about something until it's a problem, or, you know, at least just trying to use the noisy data and seeing where you end up, because it could be that you actually are going to do fine and there's something about it that actually is really beneficial to your problem. Another thing, like we saw just a minute ago, is I didn't do this exact search, but this was from before. Explore your data. So you can use noisy data, in my mind, to train models and use those models, even if it's not going to be your production model in the end, to explore your data and understand what happens when you pass that data through a model. So that's really, really important. And then there's this sort of concept, this is kind of the oldest trick in the book, of just using the good parts. So one way to do that is to learn to use the data, even if it's noisy, even maybe the labels are very noisy, if you have a lot of extraneous labels or something like that. Sometimes you can still get really good representations of your data out of it. So this is a paper from Matt Zeiler, our CEO, visualizing and understanding convolutional neural networks, where he's talking about features that can be learned from the data, and there's this really cool visualization of it. But yeah, so even if the data is not exactly what you want to train on in the end, it might be useful to get you started, to get a really, really rich representation of your input space, and then if you're able to, then you can clean the data to a limited degree and sort of fine tune on that. So everyone knows about that trick. And then the last thing I think it's useful for is just to make you think, right? Kind of like we saw in the demo. Maybe if you see that your data is not what you expect it to be, maybe you have some questions to answer about what problem you're trying to solve, right? Exactly what is this model being used for? What is the domain? What is the purpose? And when you're thinking about that problem, maybe you can think about more questions about, like, okay, who could this possibly affect, right? Are there chances of this having some kind of inherent bias, maybe machine bias problem that could really affect people's lives? Is there a possibility that there's something we didn't consider about the data, the way we collected it? And so yeah, so usually the data, the purpose of bad data in my mind is to actually give me questions instead of answer them. So what did we talk about today? So bad data, in my mind, takes essentially these two forms. There can be honest bad data, where you can train models on it and you're going to get a terrible model. And there's deceptive bad data, where you can train a model on it and everything seems fine until something terrible goes wrong down the line. You can use tools to evaluate these models. You can use tools to break through that false confidence and make sure you know exactly what your model is doing. And you can use tools to expose inherent bias in your data that you weren't familiar with previously. And if you're stuck with it anyway, you can just try to use it. You can use it to make representations, and you can use it to reconsider your problem. So thanks so much. That's all I have. This is my email. If anybody wants to continue the conversation, I would love to hear from people. So, and thank you to Data and Conf for having me. This is really, really fantastic opportunity.